Good morning everyone. The purpose of today's presentation is to make you aware of the challenges that we face during the process of heterogeneous computing. Before stepping into the challenges, allow us to introduce briefly on heterogeneous computing. So, what is heterogeneous computing? Heterogeneous computing refers to the integration of various types of processors, such as CPUs, GPUs, DSPs, and FPGAs, in a single system. Heterogeneous computing emerges as homogeneous computing hit the bottleneck, since it had problems with power consumption and heat dissipation issues. Heterogeneous computing, on the other hand, improves performance and is more energy efficient. Although there are many benefits surrounding heterogeneous computing, the challenges to implement these systems is quite a difficult task. A few of the challenges include design and development complexity, programming model and environment issues, interconnection requirements, hardware-software integration, scalability, and cost management. The first challenge we face is design and development complexity. There are several sub-challenges like designing of heterogeneous systems, which is a complex process as there is a need to optimize design to accommodate a wide range of applications. From here, to develop software to support the design is equally complex. Development of these software takes time as specialized programming languages and tools are used. Resource management is critical because the developers must make sure that the system allocates processor time, memory, and other resources that optimizes the performance while maintaining energy efficiency. It also requires solid designs and testing practices to achieve security and reliability. Up next is programming model and environment issues. This challenge arises due to the wide range of hardware components used. The developers need to possess expertise in multiple programming languages to accommodate the requirements of each processor type. The development environment should provide compilers, debuggers, and performance analysis tools to support each processor. However, achieving this is difficult because it must simplify the hardware complexities while still exposing enough details for optimization. Gaining optimal performance in heterogeneous systems requires careful task partitioning and mapping to appropriate processors, which requires models to identify which parts of the application is best suited for each task. As applications evolve, the programming model must ensure that they can scale across different hardware configurations and generations. Portability is another concern. The programming models must provide a level of abstraction that allows for portability while still enabling hardware-specific optimizations. Thirdly, we have interconnection requirements. Key challenges in interconnection includes the complex data transfer between various types of processors, where different processors have their own communication protocols and data transfer rates. The second is data transfer overhead and latency. which is caused by moving data between different processors. And finally, synchronization, which requires processors working at different speeds and with different task completion times to be coincident to ensure data consistency and correct program execution. Several technological approaches to minimize the problems are network on chip, which is efficient integration framework that uses networking principles to connect cores within a chip. And high bandwidth memory provides high-speed memory access to GPUs and other processors, reducing latency and increasing bandwidth for data-intensive tasks. Then there is hardware-software integration. Efficient hardware and software integration is the key to make the most of processing elements like CPUs, GPUs, DSPs and FPGAs in heterogeneous compute. Real-time applications require sophisticated algorithms that can distribute tasks effectively. Scalable system architectures must handle a large number of tasks and volumes of data without affecting performance. Security integration is crucial and requires a comprehensive strategy, including encryption techniques, secure boot processors, and consistent security updates. Middleware and frameworks provide common programming interfaces and tools for managing memory, scheduling tasks, and debugging. Collaboration among stakeholders is necessary for ongoing research, innovation, and standardization aimed at realizing the potential of heterogeneous systems. Last but not least, scalability is a crucial aspect for computing that refers to systems' ability to handle increasingly complex tasks and data. Various strategies can be adopted to achieve scalability, including architectural innovation, software optimization, data management, operational efficiency, and economic consideration. To achieve architectural scalability, innovative designs that can maintain performance gains when scaling up are needed. The softwares need to be optimized to make the most of the available hardware resources efficiently as system grows in size. Additionally, data scalability needs to be addressed to manage, process, and transfer data efficiently. Operational scalability should also be considered, addressing the manageability and the maintenance of systems as they scale up. Moreover, economic scalability is an important consideration, and the cost-effectiveness of scaling systems should be considered. By adopting these strategies, scalable computing solutions can meet the changing needs of modern computing environments. Final challenge is cost management. Managing costs in computing can be challenging, but it's important to consider upfront capital costs and ongoing operational expense. Specialized hardware components like GPUs, FPGAs, and custom accelerators require a significant initial investment. Personnel training and recruitment can be expensive, and operational expenses like power consumption, cooling, and maintenance make up a significant part of the total cost of ownership. However, open source software, community-driven frameworks, energy-aware scheduling algorithms, dynamic power management techniques, and advancements in hardware design offer opportunities for reducing costs. Conferences and authoritative publications provide knowledge, and best practices for developing effective cost management strategies. In conclusion, even though heterogeneous computing brings forth benefits such as greater performance and energy efficiency, the developers must undergo many challenges such as development complexity, programming modeling, and cost management, and many other. Addressing these challenges will lay the foundation for greater and more powerful heterogeneous systems in the future.